nice to meet you.
Alrighty. Round two. Welcome everybody who else came in.
We can introduce ourselves again. Yeah, my name is Matt, project lead for PhotonVision and alumnus of Team 5940.
Chris Garth, mentor for 1736 and developer for PhotonVision.
Banks Troutman, I'm a mentor of 2974, alumni of 832, and project lead for PhotonVision.
I'm Mohammed Durrani, alumni of Team 834 and also developer for PhotonVision.
Awesome. Yeah, and thanks everyone for coming. We'll put faces to names after this. I'd love to meet everyone who I've met on Discord but never actually in person yet. So to lay out some scope for the talk, we're going to be chatting through an overview of good vision practices, at least for 2024. Obviously, we don't know what 2025 and beyond is going to bring. We're going to be highlighting some common characteristics of good vision processing solutions with a focus on localization, but this isn't like a prescriptive recipe. What works well for one team doesn't necessarily generalize to every team, and so that's a really key takeaway, I think, for everyone. We're also going to be showing off how photon vision can be a key component of a overall effective robot, but obviously these strategies are going to generalize to however you guys end up doing your robot. So for some vision.
We'll start with the basics of vision, and we'll jump into that with the history of vision and FRC. Originally, the very first target that they offered for robots to view with cameras were simply very vibrant colors with some contrast between the two. And that was around 2009 where they first introduced vision. Sometime after that, as cameras became more advanced, they started putting retroreflective tape up on vision targets, a tape such that where light is shined, it comes back directly where the light source is. So you would see these bright LEDs around your cameras, shining light, hoping to get as much back as possible right at the camera. And now we have advanced to Apriltags. Apriltags are industry-wide standardized, what are called vision fiducial. And you might see these in some warehouses where they have automated robots moving around, and that it is a better target for the reason of you'll see it in the real world. Retroreflective and vibrant colors, they're suspect to lots of noise and other things. Localization is ultimately one of the large goals of looking at the world with your cameras. It's the math behind answering where am I actually on the field or in a warehouse or in the world. It works by combining information from computer vision and other sensors potentially to estimate your robot's location in this space. So why do we care about making this better? Why do we need to add more information? Hopefully we'll answer some of the how and what's in this presentation, but you'll still be responsible for determining the when. Generally, you should employ vision when it's better than other choices, and in FRC, this implies more points per second. To be better than the alternatives, you need a vision system or a component of an automation system that's faster than mechanical alignment or human play, or less stress on the humans at the robot so they can focus on the other tasks that they have to do. Achieving this can take multiple seasons, but you can't beat a human driver if it's not worth it. If your vision system is being used to enhance autonomous, it needs to improve the average points scored per second rather than simply adding variability. Alternatively, vision should be employed when you have students interested in learning about it, regardless of the competitive benefits. I get a ton out of working on photon vision personally, and it has helped me develop in my career as well.
So just kind of drive home the point of exactly what localization is, right? The whole idea is that we're trying to give your software some computed notion of where your robot's at on the field. Here's a quick video of it working on a robot right now, where as the robot drives around, on the dashboard critically, you can see the little white robot moving around on the field. Again, that's the software's notion of where it thinks the robot is at on the field, calculating that in real time as the robot moves around. This in turn is going to enable a lot of different potential really good behaviors. So for example, in this video right here, 3539, it runs into another robot and then manages to score 2 notes right after it. When it runs into the robot, you'll see it actually does get knocked off course by a decent amount. And its ability to correct for that and continue to score afterwards is primarily driven by the fact it can see the April tags there and understand where does it need to move to correct for that. Correcting for these external disturbances usually involves an external reference like a vision processing system. Alrighty, so I want to get into a little bit of what we're going to describe as the vision pipeline. And this really is, I'm going to say, by and large, how almost all teams are breaking down this problem of using a vision system in 2024. We've got the real world. There are things out there in the world that you care about. Light hits them, reflects photons into your camera. The camera is going to measure those photons. It's going to send back pixel data to some set of processing hardware and software. That processing hardware and software is responsible for analyzing the pixels and trying to figure out, from relative to where the camera is at, what does it see in the world and where is it at relative to the camera. As a second step, you will then take that information and fuse it together with other sensors to create your best guess estimate of where the robot is at on the field, that localization thing we're talking about. We'll go through each one of these step by step.
So we'll start with the camera, which is obviously how you get this information to start using it. Cameras work by projecting their current view of the world through a lens onto an array of pixels. Each pixel tells you the color or the luminance of that part of the image. Lens choices change how much light is collected and how much of the world the camera can see through that lens, the field of view. They also change things such as how fast the camera can see that light, or potentially what type of light they see, if you were, for example, filtering for infrared, though not applicable here. The sensor design of the actual pixel array can also change how fast it can collect that information, how high resolution it can collect that information per pixel, as in how much light do I have, how precise can I collect that, as well as simply how many pixels there are. So your robot probably moves around a lot. So when you're looking at camera selections, there's one thing that should be prioritized in terms of how do we make sure we get good data. You'll see in these moving circles here, we're comparing what the world might look like to a global shutter camera versus a rolling shutter camera. The rolling shutter cameras have a scanning line that moves down the array, and they collect that information at different points in time. The shutter rolls down the array. So if something's moving very fast, you might just get this big garbled mess of information, very hard to make good use of. A global shutter camera captures the entire sensor array instantaneously at that point in time. However, a global shutter camera is still suspect to motion blur when things are moving faster than it is capturing images. You don't get away from that with global shutter. You can account for that by increasing frame rate, which can be done by decreasing exposure or simply getting fancier cameras.
Yeah.
So about the exposure is how long, the period of time of which the sensor array is collecting that information to then put it in a frame and give it back to you. The higher the exposure, the more light will be collected, but that means it takes longer for each frame to come back out. Gain ISO is an internal signal amplification of the information that was collected, and that's typically represented with the brightness slider for most cameras. Combining changes between the exposure and brightness of your camera, on some there are separate gain sliders. Combining these changes can help you minimize the time it takes to capture each frame while still collecting enough good information to use in that image.
So to go along with the camera, you obviously need to use hardware to actually process the frames that you get. A big questions we get from teams is that how do I pick hardware and what hardware should I use on my robot? At the end of the day, it's trying to optimize between increasing FPS, decreasing latency, decreasing cost, and minimizing the challenge that you face when using software or the hardware. There's a lot of modern options out there for teams. We have the Limelight, which is probably the biggest, is a Raspberry Pi, power supply, camera, LEDs, and all-in-one nice package. It's great for teams if you want just like a tried and true, easy to use package. After that, we have the Raspberry Pi, which is a very popular single board computer that lets you use single CSI cameras and has pretty solid software support. The most popular option for teams using PhotonVision is the Orange Pi 5, which has better performance than the Raspberry Pi in a similar form factor. It's also relatively affordable. After that, if you're looking for even better performance, you get into the realm of mini PCs like the B-Link, where you can get better performance, but you also face a harder integration challenge. Now, obviously, we're not limited to this. There's a ton of other co-processors you could use, but these are the ones that have been tested by a bunch of teams and the most popular options, we'd say. Obviously, we do have the RoboRio, but we don't recommend that anyone does this kind of computation on the RoboRio. It wasn't meant for it. but it is still possible for teams. The most common configuration we see for teams using PhotonVision is the Orange Pi 5 mentioned previously, the USB OV9281 camera, which is a global shutter camera, and the Pololu buck converter, which is found on the link there. One quick note is that you really want to be careful about the power regulator or the buck boost converter you use on your robot. You run into a ton of random issues if your coprocessor is turning on and off repeatedly during the match due to low voltage, and you can't just pick any random one off Amazon, which a lot of teams do, and it ends up hurting them. So we really recommend go on docs.photonvision.org and see the latest recommendations for cameras, hardware, and power supplies.
Awesome. So let's dive a little bit deeper into the actual Apriltags that we've been talking about. To expand on what Banks mentioned previously, these can be thought of similar to tiny QR codes. They're specifically designed to help your robot navigate an environment where you scatter these around. They are constructed using this fixed white border on the outside that is 1 pixel wide, followed by a fixed black border just inside of that. And within those two are your ID bits. So similar to a QR code, those can encode a tiny bit of information. In this case, they encode the ID number of the tag that you're looking at. And these are placed on the field in known locations. Those are just in the game manual. In this case, there's up to 600 different tags, IDs that you can encode using that 6x6 grid of pixels there. And the corner location, the transition between this white border and this black inner border right here in those 4 corners is really critical for localization, because that's the information that we're going to feed into our code to tell us, well, we see these corners at this location, where must our robot have been?
Alrighty, so you guys all came here to talk about Apriltags, and the one thing that we were going to not recommend you do is go write software to go find Apriltags in pictures. There are libraries out there to do that. PhotonVision uses a library, WPILib provides you one. You shouldn't have to write the literal code going through pixels to actually figure out, is this pixel part of an Apriltag or not? That being said, it is useful to know what those libraries are doing under the hood, so I want to quickly go through the general algorithm that is getting used to find Apriltag in picture. Obviously, first step, take a picture. We're going to go frame by frame through the image and just go at each individual frame one at a time. So we have one picture. The very first thing we do is we look for sharp black to white transitions. So anywhere where the brightness of the pixel between the brightness of one pixel and its neighbor changes by a large amount, that's where we're going to detect where those large transitions are at. If you're in Calc 1, you could think of this like taking the derivative of the image. More formally, it's taking the gradient of the image. Once you've got those areas of high change, where the intensity changes very rapidly, you start to group them together. And there's a couple of algorithms you use to go figure out, here's a group of sharp transition. It's a small square, and then here's another group of large transition. It's a bigger square around it. You're looking for those patterns of smaller squares within bigger squares to identify what exactly an Apriltag is. When you've got a cluster of those smaller squares, you then go apply and figure out, okay, these particular locations in the image ought to correspond to the data bits inside of the QR code. Then you go measure how bright each one of those regions is. And based on whether it's light or dark, you extract a 1 or a 0 out of it to get the ID of the tag. Assuming that set of 1s and 0s does indeed decode to a valid ID, you can then go back up to the next level. And at that next level, what you're looking at is where are the corners of that outlined ID of pixels. Critically, those corners are what we're going to keep coming back to, or what are actually used for the localization. The data bits on the inside are just to get the identifier.
So everything we've done up until this point is all you really need to do visual servoing or turning toward the target like teams would do with a retroreflective tape. All you need to do is find the center of those 4 points, and that gives you the yaw of the target, or how far left or right the target is in your camera frame. After that, you can use a simple PID loop on using the yaw error and have your robot turn towards the target. This is what teams have been doing for a really long time. It's simple, effective, but obviously the whole point of this talk is that better does exist, and we do this through getting the pose of the tag in 3D space.
Right, and so the link between 2D image land, where I've got a pixel at some XY point, and 3D, like where is this thing in the real world, is linked by camera calibration. So that's the set of camera properties that describe how your camera perceives the world, specifically things like focal length. So that defines, if you're familiar with cameras, focal length is a measure of how zoomed in your image is effectively. Things like where the optical center of the lens is, all of that happens through a process, determining those numbers happens through a process called camera calibration. So that's taking pictures of a known object like a chessboard at a whole bunch of different angles and locations and feeding that into a process to then back out what your camera properties are. So there are a whole bunch of different libraries that, again, do this process. You probably shouldn't be writing numerical optimization code yourself. Things like Mr. Cow, things like OpenCV will do this for you. A really key part of this, though, is getting a good high-quality data set of these images to feed into your calibration. So that means, again, like taking varied pictures at not just head-on with your camera and the object, but like at different angles, ideally at compound angles, so not just like rotated about, horizontally or just vertically, but kind of both at once, at a range of different ranges. There's a link, again, slides will be sent out. There's an awesome link from the Mr. Cal documentation talking about how you should be collecting these photos to really cover your entire calibration space and to be getting good quality results from this process. But again, this is how we take image point in 2D space and then go back into where is this thing in 3D space.
All right. So just for a quick recap, we have April tag in the real world, our camera has seen it, and we use some sort of combination of processing software and hardware to get both the corner locations and the ID of the tag itself. From there, we can use corner information to find where the April tag actually is relative to the camera in 3D space. After that, using information on where our camera is on the robot, where the April tag is on the field, we can actually find the pose of our robot or where the robot is on the field. Before we get into that, we need to talk a little bit about the different vocabulary and coordinate systems behind all the math going on. So first, let's start with the field coordinate system. Most people agree with the field coordinate system having the origin on being on the blue aligned side no matter what, with the positive x-axis pointing away from the blue align's wall, the positive y-axis pointing up, and as you rotate counterclockwise, your theta will increase. Now, this is the convention that we follow in our examples. This is the convention that WPI follows. This is the convention that WPI follows, but technically it is arbitrary. You can set it to whatever you want, but one thing we really want to stress is that you have to be consistent with your coordinate systems. It's really easy to mess up and use the wrong coordinate system, but it's also really hard to actually debug when you do make that mistake. It's worth noting that once you know your location in this fixed field coordinate system, you can do a little bit of math to find where you are in any other coordinate system. This is useful if you need things to be different based off of like red or blue lines. Next, we have our robot coordinate system. This is fixed at the center of rotation of your drivetrain on the floor. Similar to before, we have your forward being x positive, if your y positive is left, and rotating counterclockwise will increase yaw. Again, similar to before, this is arbitrary, but this is the convention that we follow, WPILO follows, and we recommend you just follow this same convention. Next, this is the final bit of vocab we have. But keep in mind that our final goal of this is finding our field-to-robot transform, or the pose of the robot on the field. When we say pose, we're describing something that provides both the location and orientation of a frame B with respect to another frame A. In our case, we want the x, y, and theta with respect to the robot frame with respect to the field frame. And when we say transform, that's just a linear operator that allows us to go from coordinate frame B to coordinate frame A. In our case, going from the robot coordinate frame to the field coordinate frame. Just for more clarity, the dotted arrows you see here is the robot coordinate system we described earlier, with the x-axis pointed forward, y-axis pointed to the left, and
One more.
Oh,
There you go. That's the robot coordinate frame.
yeah, there's the robot coordinate frame. And just one thing to note, WPI Lib supports doing all of this in both 2D and 3D through the Pose 2D and Pose 3D classes. All the discussion we're doing today will be in terms of 2D, obviously because it's a lot easier to think about, but anything we're going to talk about will extend to 3D without losing any generality. So there's two useful properties of transforms we're going to talk about today. First is inversion. If we know the transform from A to B, we also know the transform from B to A. You have the field to robot transform, and if you know that, you also know the robot to field transform. And then we also have composition. So if you know the transform from A to B, B to C, you know the transform from A to C. This is very similar if you've taken a physics class where you do tip-to-tail vector addition. And yeah, those are the two mainly useful properties that we're going to utilize today. So the overall goal with all of this is that we want to find the field to robot transform. In order to do that, we need three things. We need to get the field to robot, we need to find where the camera is relative to the tag, and where the tag is on the field.
Right. So again, to drive home the tag locations are known, like given to us as part of the game manual, but what we need to know is like where it is relative to our camera. So remember from like camera calibration, we're talking about 2D to 3D, that's sort of how this plays in. We know where these corners are located in space, we're looking at them, so where must the tag have been located for us to have observed it at those pixel locations in our image. There's, obviously, you can't just go from 2 dimensions to 3 dimensions without losing a bunch of information. You have to make some sort of assumptions or estimates. And one of the artifacts of that is pose ambiguity or flipping. I've got a rectangle drawn here, and you can imagine that I can draw this green box and this blue box. And both of those, if you squint, look the same, right? Like maybe this is a box pointing down, and maybe it's pointing up. And then this optical illusion is what drives pose ambiguity, where you'll have a thing in your camera and it sort of like oscillates back and forth. It seems like between like pointing up or pointing down, or maybe pointing left and pointing right. And this is an effect that increases as you become more head-on with your tags. So if your camera is below the tag, or maybe you're off to the side, this is less of an issue because you can imagine that the tag looks more like a squished parallelogram and not just a rectangle, where when you're a rectangle, a little change will result in a huge change in this pose. Whereas if it looks like a parallelogram already, it's a little bit more obvious about where it ought to have been observed from.
So the camera to robot transform is really critical in this localization pipeline because, as we covered in the previous step, we now know where the camera is relative to the tag. And we want to figure out where the robot is relative to the tag so we can then find out where the robot is relative to the field. When you are designing a robot and you plan to put cameras on it, it is really, really important, if at all possible, to place that camera in CAD with its mount and take those measurements from the origin of the robot, because that information then has to be put in the code so that transform from the camera to the robot origin can be used in our transform chain to back out where the robot is on the field. That accuracy has some leeway, but most importantly, the rotations, the 3 degrees of rotation that camera can be at will have more of an effect than the XYZ translation of that camera. So keep that in mind. It is indeed possible to hand place a camera, pull out some nice straight rulers, and get it 90% of the way there. If you don't have lots of rotation, the rotations do add a lot of complexity. I would recommend, when possible, when the design allows for it, minimize compound angling of the camera, because if you do in fact lose some of that information between building the robot from the CAD, which happens to all of us, it is much harder to recollect that information once it's in the real world. So now we know the camera sees the tag, so we have our camera to tag transform. We have the camera to robot transform. We need to get the field to tag. Thankfully, this information is provided, as mentioned before, in the game manual, and WPILib every year builds a map, effectively, that gets sent out with WPILib that you can use to, based on the ID we decoded earlier using the internal bits, ask this map, where is this tag on the field? So this work doesn't have to be done by anybody, but it is an important part of the chain to find that location with these stacked up transforms.
Right, so we've sort of been beating around the bush here, but to get explicit, we've got these 3 transforms, they're nice and color coded. We've got field to tag from WPILib, camera to tag from our 3D pose estimation, and camera to robot from perhaps a CAD model or measurements that we've performed. So we're going to do a little bit of algebra now to get what we actually care about, which is field all the way on the left to robot, which is all the way on the right. Like Mohammed mentioned earlier, you can invert a transform. We represented that with like the -1 operator here, but that's flipping the order around. So now we've got, instead of camera to tag, we've got tag to camera. And then like Mohammed mentioned before, you can also compose these transforms, right? If I have field to tag and tag to camera, I can just sum them up, right? And get field to camera. And then I'll repeat the same trick just a second time to get field to robot. So this is awesome, right? This is what we want. This is where a robot is on the field. You can also see that there's a whole bunch of different places that error can creep into this. I've got an inversion here, which means that if perhaps the orientation of the tag relative to the camera isn't quite right, that's going to stack up massively when I go and invert that. Because now a little change in the orientation of the tag is going to translate to my robot just moving all over the place depending on how far away you are. And we're also adding up transforms. So the same sort of idea applies there. So really thinking about this scientifically and when I'm narrowing down where error could be creeping in, what am I doing that might introduce that, and how can I narrow down that process is going to be key to sort of debugging that. I finally have got the same code in Python, but this should be really, really similar in Java or C++. We're doing the same thing. We've got field of tag. We're using transform by instead of addition, and inverse instead of -1. But otherwise, I think that this is word for word what Java looks like.
All right, so now we have where our robot is on the field. That's pretty great, but we don't want to just use that measurement directly, because like Matt was talking about previously, there's going to be some level of error to it, there's going to be some noise in the measurement, and it won't always be 100% accurate. We want to combine that pose we get from our vision system with information we get from a variety of other sensors, like our wheel odometry, gyro, and others, just so we can get a best guess of where our robot is on the field. So how is this actually done? In both FRC and other robotics applications, a Kalman filter is the recommended approach for fusing these pieces of information together. Now, what kind of input are we talking about? Like I said previously, you can use wheel encoders, your vision system, your gyroscope, and a whole other variety of sensors. The general principle of Kalman filter is that no information is bad. As long as you can quantify how accurate your information is in terms of standard deviations, you always want to throw more information into the filter, and your estimates will only get better. However, the big assumption is that all of your estimates are clustered around some correct central value. If your values if they're centered around some incorrect value, for example, due to manufacturing error, bad camera calibration, or a variety of other things, your Kalman filter can't fix these issues. So how do we actually go about doing all of this? You just have to do some simple math, just probabilities, but we're not going to go into it. It should be self-explanatory. But in reality, you don't have to do any of this, and we don't recommend that you do any of this by hand. All of this is built into WPILib, and we strongly recommend you use what they provide so you can focus on a lot more of the interesting problems that are going on. So really, everything we've been talking about over the last 20 slides or so is this. You set up your drivetrain pose estimator. In this example, we're using a swerve drive. You add your vision measurement you get from your vision system. You update your pose estimator using your other sensors, in this example, your gyro angle and your module positions. And finally, that last line you have here is where you get your localization. You call get estimated position, and now you have the current position of your robot. So with all of that, you've now accomplished localization. Congratulations. But yeah, that's awesome. That's great and everything, but how do we actually use that data? That's a really important part in FRC. We can get the data, we need to actually use it in an effective way so we can score more points. Now we're going to walk through a few of the different strategies teams use to actually utilize their data from pose estimation.
So this example, we're going to take a kitbot robot, and knowing where it is on the field, we're going to automate a simple task for a driver. Task automation is one of the simpler things you can do with some of this information because it doesn't require adding lots of steps around it. You just want one less step for your driver. So this is this year's kitbot that was provided by First. It has a very simple launcher. The note comes in from the top and the note goes back out. There are two motors. One holds the note in and prepares to shoot it, and the other one is spun up when you want to shoot it. So this requires operator input every time you want to put a note in the goal. You have to drive there, you have to spin it up, and then you have to shoot it once it's ready. You could train at driver practice and say spin up, hit the button yourself when you're getting close to the goal, but we can make it easier. With the information of where the robot is in the field, we can decide when to spin this up automatically. So we're adding a new block here to our pipeline, and we're calling it launch control. And we want to figure out when should this spin-up motor be spinning, so all they have to do is press the button to shoot it. So here we have some Python code. We describe some information here with the is close to speaker. We're looking on the x-axis of the field, and we've drawn a proverbial line here saying, if I'm past this line, I'm close to the speaker. We create a trigger that attaches to this function. So this trigger will fire when we're close to the speaker. And while that trigger is true, we spin up the shooter. Okay. And so in that way, your driver has one less button to press, one less thing to think about, and they can focus on all the other stuff going on in the match.
All right, so this is kind of the quintessential example that most people think about when we say, oh yeah, we put localization on our robot, now it just kind of drives itself. Well, we're going to go through a little bit of how to make it drive itself in certain scenarios here. Specifically, we're assuming that you've got a swerve drive with 4 modules on it. How many people here have a swerve drive with 4 modules on it?
Oh, wow.
Yeah. All right.
Everyone? Who doesn't? Hell yeah.
Thanks for raising your hand. Okay, for the vast majority of the room, the whole point here is that fundamentally, no matter what drivetrain you got, the basic cycle is your robot drives to a spot, does a thing, and you get points. We're going to try to add some automation to that drive to a spot thing. So critically, you have to pick a point on the field where you want your robot to be at in order to score something. We're going to help reduce the manual alignment time here, or automate that step so the driver isn't sitting there kind of fiddling around, just getting you in the right position. We want you to push and hold a button, and the robot goes to the right spot. Critically, we're going to talk about simple straight line motion right now. We're not talking about path planning. We're not talking about like diving and dodging another robot. This is, you're kind of close to where you want to be at. You press and hold a button, whoop, last mile alignment right here. Again, same thing. We're going to start with the same pipeline that we have already. We have our field to robot estimate of where we think we're at on the field. We're adding a new block at the end that we're calling drivetrain alignment control. That takes where we think we're at on the field, it takes where we want to be at on the field, and then sends speed commands down to the drivetrain to actually cause some motion. And this is kind of that same diagram, but run around in a little bit of a different way. You've got, again, down here, the whole vision system we've been talking about so far. On the far side, you've got your drivetrain control. So whatever the driver joysticks are currently going into, that same software that's controlling the motion of the drivetrain, making your motors spin, actually physically moving your drivetrain around, that's all present here. What we're going to talk about is what kind of code do you put in between those two things to actually get from where you think you're at right now to where you want to be at. And again, remember, each of these poses has 3 things in it. We have an X position, a Y position, and a rotation. And the secret sauce is not all that secret, not all that complex. You take those 2 poses and you split them up into their individual components. You subtract them and you run the error through a PID controller, or really you just do a PID control with your desired and your estimate there. Again, most of the X and Y can have the same tuning, usually do. Theta's a little bit different sometimes, but again, you tune 3 PID controllers, and the output of them critically, and this is really the punchline here, the output of those 3 PID controllers is the exact same, should be the exact same commands that your driver is sending to the drivetrain. Just as your driver has joysticks for X, Y, and rotation speed, these 3 PID controllers produce that same information. So you write this code, and then you integrate it into your software by basically saying, if you want auto alignment, feed the output of the PID controllers into your drivetrain. Otherwise, just use the joysticks, and that lets the driver switch between automatic and manual mode. If you do go look in WPI lib, they've got some things called holonomic drive controllers that is pretty much just all this wrapped up into one nice class for you to use. And that's that.
Awesome. Nearly the end of content before we open things up to questions. I wanted to jump into some planned improvements for PhotonVision, at least as of right now. A big one of those is docs and examples, especially with simulation. A lot of our docs and examples were developed when a differential drive robot was looking at retroreflective tape targets. That is, as our little demo here described, no longer true, and we're definitely very much a swerve-centric, Apriltag-centric competition at this point. So making sure that that's reflected in the docs is really critical for making, I think, the software more accessible for everyone. Machine learning, we had some demoed, like beta sort of features, doing note detection, using Orange Pi 5s this year. I don't know if anyone here ended up using note detection on their robots.
Hey!
Yeah. Heck yeah.
Sweet. That's awesome to see. So trying to expand that to be on more coprocessors with more varied notes, maybe more varied models than just notes, and trying to expand the infrastructure around that would be awesome, especially looking for contributors who are excited to jump onto that. Streamlined calibration process, we've been playing with like doing better visualization of like where you've taken pictures already and where you maybe need to focus on to further to make your calibration more accurate, or perhaps assistance. We've got some toy strips, but again, need someone to help push that over the edge and make it in. And not a factory graph announcement, but I have a thing now that does localization slightly differently than the way that we've described, but at the end of the day, still does the same thing, just with more probability that I don't quite understand.
But it works better.
But it works better, and seems to address the pose ambiguity things in it by doing math in a different way. So definitely going to be a really huge season in 2025, and especially as we gear up for 2027 with the new robot controller, lots of conversations to be had around that.
All right, so one last thing, especially there's a lot of content in here, especially you saw some pictures of robots, some GIFs of things happening here. For the record, a couple of us work on teams actively right now, but it's not like we have dedicated PhotonVision robots we're developing this on. This is a community project. The people who are developing the software do it in their free time just because they like doing it. And the people who use it and test it are all of you out in the community actively doing this on your robot. In prep for this presentation, we had put out a request just saying, hey, tell us stories on what are the things that you had success with PhotonVision. So blind thank you to everybody who I saw responded. There are more people than just this. The other thing I want to make note of is a really special thank you to the teams who are talking about how they won some awards with this. It was really, really heartwarming to me personally to see that not only were you able to use the software, integrate into your robot to do cool things, but then to be able to talk about that to a judge. That was something that I thought was really, really impressive. It made my day when I saw some people saying thank you for that. So again, thank you guys for doing that. Yeah.
Awesome. And with that, everyone, thanks again for coming, and we'll open it for questions.
Sure. Raise your hand first. Go ahead first.
How do you find the standard deviations for pose estimators?
Standard deviations for pose estimators. Going back one step, one of the configurations you would pass into a Kalman filter is something called a standard deviation, which is effectively a measurement of how much do you trust this sensor? How much noise do you think is in its signal?
So that's the
This slide came in use.
No, so that's like the width of this bell curve here. I don't know if we have a better picture of a standard deviation.
I don't think so.
I know that Advantage Scope will let you do some statistics with data, I think, right?
Yeah. So if you collect camera data, just hey, your robot's sitting on the field and just look at the April tag for a couple minutes and just collect the data of your pose. There'll be some noise in that goes up and down. Hey, we do have that. You can just measure that if you want. Alternately, you can just kind of tweak and tune it. If your pose is converging too fast, just reduce or change the standard deviation so it does not converge as fast and filters out more.
Yeah.
As for the methods of collecting that information, we do have a 100 sample long standard deviation calculator in the PhotonVision interface. Yeah. And Advantage Scope has a statistics tab that you can add signals to collect that information about those values as well.
That's it.
Sure.
Will multiple cameras, like you have two mounted in front of the robot, reduce flipping, and by how much? How significant would it be to get multiple views of the April tag?
Yes, but also no. Sorry, go ahead.
Yeah, thanks.
Yeah.
So the tricky thing with multiple cameras is they are never taking pictures at the same time, asterisk, of course. You can get expensive cameras that allow you to run hardware digital lines between them to synchronize frame captures, but that's not something that we have support for on the software side, because the software also has to understand they're taking those images at the same time. Were the cameras taking those pictures at the same time, you could present all of that information to the estimator as a single frame, and it would account for that.
But they do multiple frames per second? Would that
So
one alternate that is less robust but more, we did use it back in 2022 on our robot, is if you get all of the individual estimates, all the possible estimates, right? So you have the ambiguity there, that gives you two possible locations on the field.
And Photon does tell you, if it can, it will try to tell you both of those options.
Yes. So you collect all those up, and then you say well, if I have multiple cameras seeing multiple tags, all producing multiple poses, now I've got poses scattered all over the field, but hopefully half of them are clustered in one spot, right? Pick the cluster then. It's effectively the algorithm we used in 2022. It is not necessarily academically rigorous, but it did work reasonably.
one caveat to that is you would have to wait for all of your cameras to collect information in a certain time step to then make those decisions. One thing I don't think we touched on, the multi-tag feature in PhotonVision. Mega Tag is also similar on Limelight. When you are able to see multiple tags, it understands better where it is because there's more data points, and pose ambiguity is far less of a concern.
So it's better to have one camera see multiple tags
Yes.
than multiple cameras see one tag.
Correct.
Yes.
It's. I think we can say it's always better to see multiple tags.
And
Then
With
out-
one
in-
camera.
in
With
one
one
camera.
Yeah, with it in one captured frame, more tags, more data, better pose estimate.
Yep. So
At the very beginning, you were showing the brightness and gain adjustments. I
Yeah.
also noticed there was auto exposure, which was unselected.
Yeah.
Do you have guidance on using or not using it?
don't. We should probably take that option out. There was a point in time when we were thinking for April tags, like it would make sense. The problem was that it would change unexpectedly on the field, right? If you weren't perfectly tuned in your other side, you could randomly lose, localization. So it was better to say, nope, get it fixed, run your robot around on Thursday or practice day whenever you can. Make sure you're seeing everything relatively evenly and just leave it fixed. The field is lit fairly evenly, so you shouldn't need to worry about it.
Asterisk.
Yes.
And another
Usually.
thing, auto exposure on some cameras tends to just not behave right.
Yeah.
That it's one of the things that's unfortunately out of our control in a lot of cases. Some cameras just don't play nice.
If I can extend that, I was at a event where I thought I heard a team complain the lighting was different than they were used to and had some challenges. Do you have
Yeah.
guidance on how to check that in a new environment?
The field calibration period that you get at the events is probably the best time to do that. The rulings have updated this year. You are allowed to have carts on the field, and that is especially helpful during field calibration where you're not allowed to drive the robot. So if you get like a furniture dolly and put your robot on it and just move it around the field, look at all the tags, make sure you're picking them all up from the distances you would want to. If not, adjust as needed.
The other small pitch I'll give for PhotonVision, there is a lesser used but available feature where you can, from robot code, trigger it to save images to disk. So you don't want to usually record the whole videos, but you could. You don't want to usually. But if you right before you take a shot or do something on the field, you could trigger a bunch of image saves and review them after the match to make sure that you were seeing that you're identifying the tags you thought. So,
In terms, in
Go ahead.
terms of having multiple pipelines, like one Apriltag pipeline, one machine learning pipeline, is it preferable to have two of those on one camera and switch between those on the camera, or have multiple cameras and switch between the active pipeline used in terms of stability and processing modes?
So
I would say depends. If it's not realistic or feasible for you to get multiple cameras in the locations you want them to do that, that might make the most sense to switch between the pipelines as needed. There is a delay when switching pipelines where you will get information as things are broken down and then reset up with the new pipeline. So that's something to be made aware of.
Yeah.
But generally, and specifically, you mentioned ML, which is only on the Orange Pi right now. It is powerful enough to handle two cameras at once without issue.
And usually the goals are pretty orthogonal, right? You're looking down at the note but up at the tags. But I would say do some science yourself.
Depends on the camera, the field of view,
Yeah.
and what your needs are specific to your robot.
Andy, back.
So, given Apriltag configuration in the current game, what sort of accuracies are you able to achieve with a static or dynamic sense?
I don't know if we have great numbers for that, but one of the teams local to my team in Georgia, 1771, they are heavily dependent on localization, and most of their tasks on the field are completely automated using their cameras. If it's feasible to go find them and ask their programmer about it, I'm sure they can give you some kind of numbers, but I would say they're within an inch probably everywhere on the field.
Yeah, incidentally, within the Peoria area teams, inch to half inch was the best resolution they could, or the best on-field resolution they would get. And again, all the assumptions of what is your camera, how fast are you processing, how good is your Kalman filter, all that plays into that number.
And I'll footnote that 1771 has gone the way of very powerful mini PC, multiple 3-digit cost cameras running at high resolutions at high frame rates. So it's possible to get about as much resolution as you want. You just have to put the work and some of the dosh up for it.
So,
Should do something back next time.
Global shutter versus rolling shutter. So
Yeah.
from what I can tell from like just looking at cameras, the highest resolution you can get within a reasonable price with global shutter is the OV92 whatever. It's like
Yeah.
50 vertical pixels, right? But rolling shutter has a lot higher resolution. So have you seen any like good trade-offs where if you have a high resolution picture, you can offset the sort of
Offsetting these effects is usually best helped by frame rate, which usually, you're fighting frame rate and resolution. I'll make a call out again, mentioning 1771, and when my team was testing vision as well. C3 cam, the 24 CUG model. It's not cheap. But it is under $200, I believe, around $150. It is a 1920 by 1200, 60 FPS global shutter camera. Again, you will need a much beefier processor to make full use of it, but if you're looking for high resolution global shutter, that's one of the ones that's known, tested, and good.
But like teams have had plenty of success using just OV9281s.
Absolutely.
So I would challenge the push towards ever increasing numbers, unless given like data that shows that that's strictly necessary for your robot.
the other flip thing too is if you did, for whatever reason, end up with a rolling shutter camera on your robot, one way to get around, and you are seeing these effects of like, you're blurring or smearing or something like that, if your drivetrain's being commanded to be moving, just reduce how much you trust your Apriltag estimates and trust them a lot more when you're stationary. There's another way to get around that.
Yeah. Someone in the back?
Yeah,
Yes.
in the back, and then one over there too, right?
With regards to ambiguity of Apriltags, have you thought about introducing a filter, like if you know that your camera will always be below the Apriltag?
Yes.
There
was, short answer is yes. There was a class put in last year, 2 years ago? No, I think it was 2 years ago now. Called Photon Pose Estimator. Is that right?
So
It was an implementation of a bunch of filtering strategies like that. We didn't know at the time what the right answer was going to be, so it was very open-ended. But
I might have ended up doing closest to floor height. Did we ever?
There is a closest to floor height estimation strategy in that estimator. However, if you cannot use that at the same time as multi-tag. So you kind of have to pick one. If you are assuming that you're only going to look at one tag and you only care about one tag, that is a valid way to combat that, is the closest to floor height estimator method.
yeah.
Yep.
I know you guys have two different detectors, the Aprilabs detector and the Artichoke detector. Do you know what detector most teams are using and which one you would recommend and what the actual differences are between them practically?
I don't know that we have a whole lot of data on who's using them.
Mechanical Advantage did a bunch of profiling though, right?
Yeah.
I can talk a little bit more about like the differences between them. For what the end user cares about, you're going to get higher FPS with the Uruko pipeline, but generally lower accuracy. This isn't exactly quantified, but this is kind of what you'll see. But I would say from what I've seen, most teams are using the base Apriltag pipeline, and that'll give you generally lower FPS but higher accuracy in terms of like the actual location you get from the corner pixels. But it's something that's like I would recommend your team test. It's pretty easy to switch in between, but that's generally what we've seen from teams.
Awesome. And so like one more minute, just
One more question, then one more quick question will head out. Go ahead.
So yeah, a quick question. Just like I remember in like the common filter, you guys like incorporate like multiple sources of like information like improve the estimate.
Yep.
Like, is it possible to like also incorporate like information from like previous frames? So let's say in one frame suddenly like the estimate by like the vision system gets like, messed up really bad. Like, is it possible to kind of like incorporate information from like the previous frames and kind of like so that way you know that like that really messed up frame is like kind of like bad enough.
So we sort of, the column filter sort of does that right now. I think what you're describing is perhaps closer to how filter graphs work, where you're looking at like the actual pixels instead of just the pose that it gives you. Why don't we talk about this more offline?
Yep.
That's the cop-out answer. Speaking of which, I think we are out of time officially. Thank you again to everyone for coming, and we'll hang out in the hallway for more questions. Thank you.